Hey there, in this video we are going to look at transformations of exponential functions, or specifically how changes in the equation are connected with translations, expansions, compressions, and reflections in their graphs. So before we start looking at transformations with exponential functions, I'm going to make the assumption that you've either watched my previous video or you've learned elsewhere about basic exponential functions like the one that's on the screen, which is y equals 2 to the power of x, about why they look the way they do, some of the features, as well as how changing the base affects how the graph appears, which what I'm doing right there, changing that base b. You see what's happening. It either goes up to the right if the base is bigger than 1, down to the right if the base is smaller than 1. But for more detail on that, of course, watch the previous video. Now, I'm going to make the assumption as well that you've learned about how changes in the equation affect transformations in the graph for functions in general, either from my set of videos on transformations of functions in general or elsewhere. So then, given all that, we're going to look here at applying those transformations that I mentioned earlier to exponential functions. So things like vertical expansions, vertical compressions, vertical reflections, as well as horizontal shifts or vertical shifts, and so on. All right? We're going to look at it in several different ways. We're going to do that right now. So in applying transformations to exponential functions, we're going to start by identifying changes in the equation and think about how that would change the corresponding graph. So for example, when we have y equals 3 to the x, and we make the change to y equals 3 to the x minus 2, or in other words, if we replace the x with x minus 2, what change happens in the graph? Well, changing x to x minus 2 causes a horizontal translation, which I'm going to abbreviate that way, horizontal translation 2 to the right. And in the next one here, if we take y equals 0.5 to the x, and we change it to y equals 0.5 to the x plus 4, adding that 4 onto the end of that function is going to cause a vertical translation of 4 up. And the third one here, if we change y equals 7 to the x to y equals 1/10 times 7 to the x, in other words, we take that function and multiply it by 1/10, that is going to cause a vertical compression. I'm going to abbreviate it that way, vertical compression by a factor of 1/10, right? Squish all the y values. And if we make the change from y equals 1.12 to the x to y equals 200 times 1.12 to the x. In other words, if we multiply that base function by 200 in front, that is going to cause a vertical expansion by a factor of 200. And these last couple here, if we take y equals 1/5 to the x, we have two changes there. We have x being changed to x plus 1, and that is going to cause a horizontal translation of 1 unit to the left. And we also have the function, we're subtracting 3, the end of the function, that's going to cause a vertical translation of 3 down. And the very last one here, two changes there. Well, you can think of it as two changes. I'm going to think of it as two changes. The fact that we're taking this 2/3 to the x and multiplying it by 4 is going to be a vertical expansion by a factor of 4. And the fact that we're multiplying it by a negative is also going to be a vertical reflection over the x-axis. All right? Now let's look and see if we can graph a few functions that have had some transformations applied to them. So this first one here, y equals -2 to the x plus 5. We're going to work from the base function of y equals 2 to the power of x and then look at the changes that have happened. So this negative in the front, multiplying it by -1 in the front, is going to cause a vertical reflection. So I'm going to put that down here, vertical reflection over the x-axis. And this Plus 5 on the end is going to cause a vertical translation of 5 units up. So just thinking my way through it first, I know that instead of going up to the right like this, I know it's going to be reflected and it's going to go down to the right. And then it's also going to be shifted up 5 units. So this horizontal asymptote is going to be right here. So I'm going to draw that in right now. And then what I'm going to do is just graph the function 2 to the x upside down from there. And then I've already dealt with those transformations. I'm going to put a few points on to kind of locate where I am. The y-intercept would have been, if it was just the basic 2 to the x graph, would have been 1. In other words, 1 above the asymptote right there in the middle. It's instead going to be 1 below the asymptote. So I'm going to put a point right there. And then we can put a few other points in there. The next one would have been 2. And the next one would have been 4. And then 8 is going to bring me to about there. I guess I could fit one more in here, which is 16, which is going to be all the way to there, I believe, if I've counted correctly. And that's going to give me that curve on that side. And then while I'm at it, I'll put the ones on the other side because they would have been 1/2, 1/4, 1/8, and that's probably good enough there. So we'll try to draw a smooth curve through all those points. And on this side, I'm going to try and draw it getting closer and closer to that asymptote as best as I can without touching it or curving away. That's about as good as I can do to show what's happening and show that those continue. So that's the graph of that function. All right, let's look at the second one here. So our base function here is y equals 1/3 to the x, but a couple of changes have happened there. We have, instead of x, we have x plus 4. We've replaced x with x plus 4, and then we've multiplied the whole thing by 4 in front here, right? So there's a 4 in front there. So what we have is two different changes there. That is going to be a horizontal translation of 4 to the left. And then this 4 right here is a vertical expansion by a factor of 4. So I'm going to think about what my base function looks like. Y equals 1/3 to the x. 1/3 to the x. We can start with that y-intercept there. And it would normally go, when I go 1 this way, it's 1/3. When I go 2 this way, it's going to be 1/9. It's going to really quickly get down to that axis there. And the other way, we got to think about the reciprocal. So it's 1/3 to the -1 is actually 3 to the +1, which is 3. And 1/3 to the -2 is actually 3 to the +2, which is 9, which is right there. And the next one, 27, would be off the graph, so we're not going to worry about that. Now, that's if I was just graphing this. So I have to do a couple of things there. First of all, I need to deal with this multiplied by 4 in front. Now all that's going to do is multiply all these y values here. So my y values here, this value that's 3 is going to be 4 times as much. So instead this is going to be 12. That value is going to be there. This value that is 9 is actually going to be 36. It's going to be off the graph, so I'm not going to worry about it. All right. This graph that is 1 is going to be 4, so that's going to cross there. And the values on the other side, well, this value that's 1/3 is going to be 4 times as much, so it's going to be 4/3, which is 1 1/3, so it's going to be about there. And then this one that's 1/9 is going to be 4/9, so maybe about a half, and that's probably about as much as I can do. But now we haven't dealt with this part of it, which is the shift to the left. So if I shift that to the left, each of these points is going to go 4 to the left. That one's going to be there. That one's going to be there. That one is going to be there, and so on, right? And then this one's going to be right there. And we can draw that curve in from there. All right, so it's going to be, as best as I can, do a smooth curve here like this. And then it's just going to be like that. It's going to keep going. I'm doing my best to get it closer and closer like that. All right, so that's what those two curves look like. Now let's do the reverse of this. Let's look at some graphs and try and write the equation for them. All right, so we're looking at how the solid line on the graph here, the graph in blue, has been changed from the basic exponential function that's shown as a dotted line. Now the first thing you want to try and determine as the base of this exponential function. And you know it's an exponential function because it has this asymptotic behavior there where it gets closer and closer to that line. Now we can use that line as a kind of a reference point to help us come up with the base. Now you can identify a few points where it actually passes through grid points. That one, the next one looks like it's about there, right? That's a distance of 1, 3, 9. So you start to think that sounds like a base of 3. And in fact, you would be correct there. But then the other thing to recognize is that this asymptote has moved down 4 units there. And so the equation of that function is going to be not just the basic 3 to the x, it's going to be 3 to the x minus 4 like that. Now not 3 to the x minus 4. The minus 4 doesn't go with the x. It's at the end of the function itself because it's a vertical translation of down of 4 units. If we look at the second one here, so we have a couple things happening there. We have this y-intercept here is 3 instead of 1, so that's starting to make me think that there's a vertical expansion because normally the y-intercept is 1. And so if we look at those numbers, we have 3 there. This is 6. This is 12 up to that point. So those numbers start to make you think that if it has been vertically expanded by 3 from there, you can see these points here. This is a 1, this is a 2, this is a 4, and each of those has been expanded. 1 becomes 3, 2 becomes 6, 4 becomes 12. They're all 3 times as big as they were in the base function there. So the base of that function is 2 because you have 1, 2, 4. This one would be 8 there. So y equals 2 to the x, except we have this vertical expansion by a factor of 3, right? Everything's 3 times as tall there, times 3, all right? 2 more here. If you look at this, you have 1, you have 2, you have 4, you have 8 on that base function. Or you could look at the blue curve if you don't recognize what it is, because you also have 1, 2, 4, 8, like that. And so that suggests to you that the base is 2. And if you're trying to work with this then to think about what's happened, there's actually 2 different ways you can look at the transformation on this graph. You can look at it as though it's been vertically compressed by a half, because all of these points, that point is normally 1, it's a half as much. This point is 2, it's 1 instead. This distance here is 4, it's 2. This distance is 8, it's 4. So one option here would be to say that this is like y equals 2 to the x, but compressed by a factor of a half. The other way to look at it is to, you might be surprised to find here that if you think about those points, you can just look at them as though they've been shifted, because this point you could think of it as shifted over to there. This point you could think of it as shifted over to there. This point you could think of it as shifted over there, and even this one up here, this 8, that's been shifted. So the other way you could write this is you could write it as y equals 2 to the x, but shifted 1 to the right, so you could make it y equals 2 to the x minus 1. And you can actually show that those two things are the same algebraically just by using some exponent laws that you've seen before. If you take 2 to the x minus 1, so that expression 2 to the x minus 1 I could write as 2 to the x times 2 to the minus 1. And 2 to the minus 1 is like a half, right? So I could write that as 1/2 times 2 to the x, and then of course that's the same as that, just in a different order, all right? The last one here. So this base function here, if you look at the distances, that point, we have 1, 4, right? And you can see that in the curve here too, 1, 4. And so the base we think is 4. So we're starting out with the base function of y equals 4 to the x. And we're making some changes to that. Now, it actually has had 2 different changes, 2 different reflections actually. Instead of going up to the right and going to infinity as you go to the right, it's going to 0 as you go to the right. It's going to the x-axis, so instead it's doing this, right? So that's a horizontal reflection, and the way you achieve a horizontal reflection is you replace x with minus x. So if we have a minus up here with the x value, that gives us that horizontal reflection. But then also it's had this vertical reflection down to there. And the way you achieve that vertical reflection is you put a minus in front of the thing to get both of those reflections. Now there is actually one other way we could write this. You could also actually write this as y equals negative 1/4 to the positive x, because this red curve here, that red curve is just 1/4 to the x, right? Because this curve 4 to the x and 1/4 to the x are just mirror images across the axis there. So you could also write it like this. Either one of those two ways is correct. All right, let's try and summarize some of the ideas that have come up in the things that we've done here. So if we think of some of the changes here, we're going to focus on the ones that come up most often. Multiplying the function by a number in front, we're going to call a. Adding or subtracting a value to x, which we're going to call c. Changing x to x plus c, or adding or subtracting a number in the end plus d. Each of those parameters affects the graph in a different way. We'll focus on that a value first. The value of a causes a vertical expansion if the value is greater than 1, the absolute value. Not worrying about the negative or positive aspect of it, but if the number part is bigger than 1, it causes a vertical expansion. And if a is less than 1, the absolute value is less than 1, small number, it causes a vertical compression. And of course, if that value is negative, if a is less than 0, it also causes a vertical reflection. Now b in that, b is of course the base of that exponential function. And as we saw in previous video, if the base is bigger than 1, it goes up to the right. And if the base is smaller than 1, it goes down to the right. The variable c up here, x plus c, c causes a horizontal translation, horizontal shift. If c is greater than 0, the shift is to the left. As in the way I have it written here, x plus c, if that is a positive number and they're x plus something, it goes to the left. And if c is a negative number, it's going to say that x minus something, the shift is to the right. And then the value of d here, d causes a vertical shift, vertical translation, adding a number onto the end there. And of course, if d is greater than 0, the shift is up. And if d is less than 0, negative, the shift is down. All right. Now, before we're done, we're going to think about how these values might affect the various aspects of this graph. All right, so first of all, which of those values affect the asymptote, where it's located? Well, the asymptote is affected when the function is shifted up or down. It's not affected by changing the base. It's not affected by shifting it side to side. It's not affected by vertical compressions or expansions. It's affected by vertical translation, so that's that value of d on the end. That changes the location of the asymptote. And which of those values affect where the y-intercept is? Several of them can affect where the y-intercept is. In fact, a, c, and d can all affect where the y-intercept is, because if you multiply by a number in front, you can expand that y-intercept to be not 1, to be a bigger or smaller value. If you shift this side to side, which is what c does, that can affect the y-intercept. And if you, of course, shift it vertically, that changes the y-intercept. So all three of those do. What happens to the graph if a has a negative value? If a has a negative value, of course, it's a vertical reflection that the graph undergoes. And which of the values affect the range of the function? If you think about that, the ones that can affect the range of the function, first of all, d can affect the range of the function, because as you vertically shift the function, of course, the start value or end value for the range is going to be affected, but also the a value. So both a and d affected. The way a can, not because it can expand or compress the function, but if there's a reflection, then that is going to make a change, right? So if it's a positive value, then the range is y is greater than or equal to that positive value. If a is negative, then the range is y is less than or equal to that positive value because the graph is below the asymptote. Any of the values affect the domain of the function? Well, no. The domain is always all real numbers and doesn't change because for any exponential function, you can substitute in any x value you want. And then lastly here, how are the asymptote and the range related to each other? Well, the asymptote is located at the end point of the range, right? That's the boundary of where the graph is on one side or the other of that thing. All right, so that's a look at transformations of exponential functions.